This presentation is delivered by the Stanford Center for Professional Development.
Alrighty, so a couple things to cover real quickly. Last time we talked all about methods and some more about objects. There's two things you should know in the programs that you're going to be doing. We talked a little bit about one of them last time in terms of how to get input from the user. There's these functions that you should know about. One is called readInt, and there's some prompt inside double quotes that you give, and what that does is ask the user basically for an integer and gives you back some value that you can say assign to an integer. There's also a version of this to get doubles, which surprisingly enough is called readDouble, and has exactly sort of the same property. So it's called readDouble. It has some string here as its parameter, or some text here as its parameter inside double quotes, which it displays to the screen and then gets you back a value, which is a double, and you can assign to a double. So those are just two things off the bat that you should know about, because that's how you're going to get input, at least for the time being, from the user in a lot of cases. Now, one thing you want to do once you actually get some input from the user is you want to do some manipulation on it, like some expressions that we talked about last time. We talked about some of the different operators like addition, subtraction, or unary minus, it's the same symbol, multiplication, division, and my favorite, the remainder. And so we talked about all of those except for this little guy last time. All of the operators kind of work the way you would expect them to, okay? And we'll talk a little bit more about division in just a second. The interesting thing about division, so all of these things work with both, or I should say all of these work with both integers and doubles. The remainder, as we talked about, only works with integers, right? Because it doesn't make sense to have a remainder when you have real values. And these three guys work exactly the same for integers and doubles, just the way you would expect addition, multiplication, all that happy stuff to work. Division kind of rears its ugly head because it actually works slightly differently if you're doing division for integers versus doubles. Okay? And the whole point of that is if you're doing a division and the two arguments that you're dividing, right, if both of these things are integers, in this case I have integer constants, which are just what I mean the values, right? If both of these are integers, what it does is integer division, which means it does the division and throws away any remainder. So what you get back is an integer. So 5 divided by 2 when these are integers gives you back the value 2. That little remainder thing is just gone. If you want to get the remainder, you use this guy. Okay? If either one of these particular values happens to be a real value, like a double, then it will do real value division and give you back a real value. So if you happen to divide 5, even if 5 is an integer, by the value 2.0, and so it knows it's a real value because it's got a decimal point in it, this will give you back 2.5 as a double, and so you can assign that to a double. Okay? So if either one of the arguments is a double, you get real value division. If they're both integers, you get back the integer portion.
I'm sorry, I was just a little confused about the double. A double is just a real number?
It's just a real number, yeah. Yep. So another thing that kind of comes up when you do expressions, yeah, sometimes you're taking notes and you just don't know. It's like candy raining from the sky. The other thing to keep in mind is just like arithmetic, sometimes you want operators to evaluate in different orders. So there's an order of precedent for how these things actually evaluate in case you have to have some big honking expression. And the order of precedent is you can have parentheses. Parentheses are the highest precedent. That means you evaluate everything in parentheses first. Then multiplication, division, and the remainder operator have the same level of precedence. And so if you have multiple of them, they're evaluated from left to right. And then addition and subtraction. Again, if you have multiple of them, evaluated left to right. So it's just like regular rules of precedent in algebra, which hopefully you're familiar with. But to make that concrete, let's say you have some integer x, and we say x equals 1 plus 3 times 5 divided by 2. How does that actually evaluate? Well, first of all, we say, do we have any parens? No, we don't have any parens. That would be the highest level of precedence. You can always force something to evaluate more highly by putting it in parens. So these guys are all at the same level, so we evaluate left to right. So we come across and we say, hey, here's multiplication. We evaluate this thing as 15, right? We don't do this addition first. This 3 times 5 becomes 15. Then we divide it by 2. And you remember what I just said. Hey, this is an integer, this is an integer, so this is integer division. So 15 divided by 2 in integer division is 7, rock on. So this whole thing is 7, and then we add the 1 to it because addition has the lowest level of precedence of all the operators here, and what we get at the end of the day is that x is equal to 8. Okay, hopefully you can see that, and if you can't, I will just tell you x is equal to 8. So know the rules of precedent. They're exactly the same as hopefully you know from algebra. It's nice to clarify. It's nice to always put in parentheses. Sometimes you have to put in parentheses to get the right thing to compute, and I'll show you that in just a second. But it's nice style just to fully parenthesize everything.
Where do exponents fall in there?
There is no built-in exponent operator. Okay? So if you're sort of like a MATLAB person or something like that, there's functions that we'll get to later on that compute exponents, but there's no built-in primitive operation for exponents. Okay? So with that said, sometimes there's times in life when you say, hey, but Meron, I have these two integers, and I really want to get some value back, which is some real value, right? So what you can do is, let's say I have int x, okay? And let me give x some initial value. So I can say x equals 5. And then I want to take like half of that and assign it to some double y. So if I say double y equals x divided by 2, you might think, hey, this is a double, right? Isn't it going to do the right thing and give me back 2.5? No. It evaluates the right-hand side first and then assigns it to the left-hand side. So you have 5 here. That's an integer. This 2 is also an integer. It does integer division, which means you get 2. Once you get that 2, it says, hey, put that 2 into a double, and says, okay, it's 2.0. So you're like, huh, that was totally weird. But that's because it was doing integer division. So what you need to do is you need to tell it, you need to say, I want you to do real value division by temporarily treating one of these things as a double. And that's something that we refer to as a cast. It's kind of like if you're making a movie and you need to come up with a cast. And you get someone who's going to like play Harry Potter for you, but he doesn't really wear glasses. And so you say, for the purposes of being in the cast, I'm going to put some glasses on you. For this one thing, you're going to wear glasses and then we're going to take them off. So it doesn't change intrinsically who you are. It just makes you appear different for this one operation. And the way we do that is we specify the type that we want to cast to in front of the thing that we want to cast. So we would say double x divided by 2. And all this means is take this thing, which is not normally a double, and for the purpose of this operation, treat it as though it were a double. It does not change x from being an integer intrinsically. X remains an integer after this operation, but now it becomes 5.0, and when we do the division, we do real value division, we get 2.5, and that's what goes into y. Okay? So that's what's called a cast. You can also do that, interestingly enough. So let's say you did that, and now y is some box somewhere that has the value 2.5 in it. And you say, you know what, I really like the integer part of y. And so I'm going to have some integer z, and I'm just going to set that to be equal to what I would get if I cast y to be an integer. Well, if I cast y to be an integer, you might say, oh, Meron, does it round? Like, do I get 3? Because I remember if it's a 0.5, we round up. That was always the way it was when life was good. No. You don't round up. As a matter of fact, it could be 2.9. It could be 2.99999. You still don't round up. This computer science, it's not necessarily forgiving. We always round down. You take the integer of a real value, it truncates. It drops anything after the decimal point. Doesn't matter how big it is. Sorry, it's just like, it's like the dollar. We just devalue your currency, right? It just drop everything after the decimal point. That's life in the city. Okay? So, if we go to the computer for a second, we can put this all together in a little program and actually see what's going on. So I wrote a little program that averages 2 numbers, and it's running right now. I'll show you the text for that program over here. So here's some program, average 2 integers. I said this program averages 2 numbers. I read in one integer from the user. I read in another integer from the user. And then I come here and notice I commented for you that it's buggy. I say, hey, the average is just adding the 2 together and dividing by 2, right? That's what I remember was the mathematical expression for average of 2 numbers when I looked it up in my book of mathematical expressions for averaging 2 numbers. And then I write out the average. So what's the problem here? Yeah, so there's 2 problems here. Dun, 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 and then we reveal the comment, and there they are. First, we need to parenthesize the expression, because in terms of precedent, the division has precedent over the addition. So if we were to say take the average of 5 and 6, we don't get 5.5, we get 8. Why? Because it took half of 6, it took that 6 and divided it by 2, and then added it to the 5. So it's actually doing this operation over here first, and we want to say, hey, add some parentheses to force the addition to happen first. Now, even after we force the addition, this whole expression here is still going to be an integer because it adds 2 integers. That's just going to give us an integer back. And then we divide that by an integer. There's 2 ways we can fix this. One is we can change the 2 to a 2.0. So we can explicitly say that that constant in there that we're dividing by is a real value, and that will force real value division. Another way we can do it is to say treat this whole thing as a double for this operation. So after you add those numbers together, you get something which is the total of those two numbers. Treat that total as though it were a double, and then do the division. So if we do that, then we're good to go.
If you put a double in there, you still need that other double before the average?
If I put a double in where?
Where it is now. You still need that other double there.
Yeah, because this is the type of average, right? So if average is not, I need to declare average first of all, and I need to give it a type. So if I don't give it a type double, it can't store a real number anyway. So that's what that double's about.
So when you put a cast a double, does it affect everything after the double on the line?
Yeah, it affects the most immediate thing after it. If it's parenthesized, it's a parenthesized expression. If it's just one variable, it's just that variable.
If the user enters a double instead of an integer, what does it do?
Good question, because someone wrote this little read integer for us, so let's run it and see what happens. Because it's just that smart. So here's N1. We're like, hey, here's 5.5. I want 5.5. And it says illegal numeric format, right? It just has this big cow. It's in red. Right? All that means is I wanted an integer. You didn't give me an integer. Give it to me again. And notice it prompts you again. Then you're like, okay, sorry. I meant the letter A. It's still illegal in numeric format. I would do that with like my friends' computers. Like, they would write their programs and they didn't do like nice error checking or whatever that all the read-in stuff gives you. And they'd be like, give me an integer. And I'd be like, how about A? And they'd be like, well, that's not an integer. And I'm like, to me it is. And I put it in, watch their program crash, and, I was mean. Yeah, there's 5.5. It's working now. You laugh now. Wait till I do it to you. Pardon? There's something you can do in Java having to do with formatting. We're not going to get into that now. If you're really interested, you can come talk to me afterward. Ooh. That's going to be the goal for this class, to see if I can get one to stay up on the camera. All right. So with that said, hopefully you kind of understand the notions of casting for an operation and the rules of precedent that are actually involved. There's a couple of shorthands you should also know. In that particular case with Z, you can skip the cast because it says, hey, if you have Y here and you want to assign it to an int, the only way I can do that is to cast it automatically to be an int. So it'll do it for you automatically.
So it's like the type that I wanted to return is sort of contains less information than I expected.
Yeah, so over here, if you add a double and you try to assign it to an int, you can't because it doesn't have space to store what's after the decimal, so it just truncates it for you. Yeah, I just put in the int to be explicit about the truncation. There's a couple other things we want to do which are shorthands for arithmetical expressions, because there are some arithmetic expressions, arithmetical, is that even a word? Arithmetic expressions, you got to keep me honest. Sometimes I just make up words. I'll tell you stories about that at some point, but not right now. Let's say we have int x, our old friend. After I told you all this stuff, good variable names, I'm like, everything's x. So let's say we say x equals 3. Now, there's a lot of things sometimes we want to do with x. Some things that we want to do a lot is to add 1 to x, right? So if we wanted to add 1 to x, how do we do that? Some people already know. We'll do it the long way. X equals x plus 1. Right? That adds 1s to x, stores it back in x. Turns out this notion of taking a variable, adding something to it, and storing it back to itself is very common, and so there's a shorthand for doing that, which is x plus equals and then some value. So if I change this, say, to a 5, and I said x equals x plus 5, that's the same thing as saying x plus equals 5. It just means take that value that's over here and add it to x and store it back into x. In the case of adding 1, it's not adding 1 because oftentimes we want to count. It's something we do so often that there's even a special shorthand just for adding 1, which is x plus plus. And this may look a little familiar to you from the Carol world. You're like, oh, I remember I plus plus. Is that the same thing? Yeah, you were adding 1 to I in Carol's world. Here you're adding 1 to x. So there's no spaces here or anything. X plus plus just means add 1 to x. And if you ever heard of the language C and C++, that's where C++ gets its name from. They sort of started with C and they just made it a little bit better by sort of doing a plus plus. Okay? You can also do sort of subtraction in a similar way. So if you want to subtract 1 from x, that's the longhand form of doing it. You can say x minus equals 1, which is a slightly shorter hand, and there is a complete shorthand for it, which is x minus minus, which means subtract 1 from x and store it back in x. Okay? There's a couple other shorthands. You can also think about multiplication. So if you want to say x equals x times 2, like you want to double 2, you could say x times equals to, same sort of effect. So there's a times equal. There is no super shorthand for, times equal to that just stops there. There was also a divide equal, as you can imagine. So x equals x divided by 2, x divide equal to. And, the value here is basically the value there. So if you want to multiply by 5, you would just put a 5 there. Same kind of thing. But these are little shorthands. You can use these with integers. You can use them with doubles. They work for both. You're fine. Okay? So besides the shorthands, these are just some little syntactic things you should know, right? Hopefully all these things are fairly clear and they make sense. There's also a notion, kind of time for a new concept. The notion of a constant. Oh, I'll write it in big letters. And the idea behind a constant is it differentiates it from a variable in that it does not vary, right? Variables vary, constants remain the same. And so you might wonder, why do I care about what is a constant, right? Like, isn't the value like 3 here a constant? Yeah, but some constants are meaningful, and sometimes you want to give them a name. So for example, pi, right? Pi is some constant that has a value like, let's just say for right now, 3.14. And so in your program, you could have some double, call a pi all uppercase. That's the convention we'll use for constants, is they're all uppercase. Separate words have underscores to differentiate them. Equals 3.4. And you might say, oh, that's great. Now, anywhere in my program, like if I'm computing like the area of a circle and it's pi r squared, right? I could just say something like, take the radius, multiply it by pi again, and this would be, my, assuming I had r somewhere and I have area, I could compute it like that. Oh, and isn't that so good? Is my program's readable? Now I know it's, yeah, that's all wrong. No one says anything. Like sometimes I got to throw things out just to be like, is anyone paying attention? Yeah, we just square pi. Pi r squared, remember that? Yeah, there's r times pi. I can just do this for computing the area and everything is just fine, right? And it makes it a little bit more readable. But the problem is, pi is a variable here, right? Nothing prevents someone from coming along and saying, yeah, you know what? Yeah, I don't really like your pi. I like my own pi. And my pi is 6 because it's just bigger. Right? So then you go compute the area, and your area got a whole lot bigger. And you're like, why is it so much bigger? I don't understand. Right? Because someone changed your pi. Get your hands off my pi, all right? And the way you want to do that is you want to force pi to not change. You want to tell the machine, this is a constant. I will give you a value. It will remain unchanged. And the way we do that just happens to have some sort of bulky syntax associated with it. But I'll show you what that looks like. Okay? So the way we say that, sort of follow along. First, we say private, because we want to keep our constants to ourselves. So what private means is this constant I'm going to define. I'm going to define the constant in a class. It's not defined in a, you can define one in a particular method, but generally we define our constants in our entire class. I'll show you where they go in just a second. And we say private because we don't want anyone to be able to see our constants outside of our class. So first we say private. Then we say static, which is just kind of a funky word, which means that this constant sort of lives for the class, and there's only one of these for the whole class. So it's not like if you're an object of the class, you don't have your own version of pi, and some other object has their own version of pi. The way you can think about it is, remember I told you like a couple days ago, you're all objects. You're all objects, and we have one constant, which is the amount of mass in this world or universe, right? And so you don't have a separate mass, and I'm like, hey, I have my different amount of mass for the universe, and it's different from your amount of mass for the universe. We share the same mass for the universe. So all of humanity, or you could think of all objects that exist, share the same mass for the universe. That's what static means. Everything of a class shares the same thing. You don't have, each object doesn't have its own version. Okay? Then we say final, which means get your hands off my pi. I'm going to give you a value, and it's the final value. No one else is going to be able to give you a value of this, because the value I give you now is the final value. Then we specify the type, right? So we'd have double for pi. And then if we can zoom out a little bit, that's going to be a 2-board extravaganza, because it's just that big. Public or private, static, final, double, name of the constant, pi, and then its value. 3.14. So all of that means you're going to get something who's of type double. Its value is not going to change after I give it its initial value. There's only one of these for the entire class, and it only lives inside the class. But we just put all those things there just so you know. Okay? Now, the important thing about doing this is you want to give your constants good names. And well, good names is one reason, right? So when someone reads your program, they can say, oh, he's multiplying by pi. That's a good time. The other thing is that it allows the program to change easily, right? So I could have area computed somewhere, I could have circumference computed somewhere else that also uses pi, I can go somewhere else and do something else funky with pi, and then someone comes along and like some physicist comes and sees my program and says, oh, you must be an engineer, right? Because you're like 314. Like in physics, if we say 314, like particles miss each other when we accelerate them to the speed of light. You're like, well, don't accelerate particles to the speed of light. But they come along and they say, no, 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 no. Pi is 3141596 2, 2. There's always a 2 before the 6. 2. I'll stop there. I have a friend who actually has pi memorized to 400 digits. I was like, that was just a tremendous waste of your time. But that's okay. I'm sure it's probably useful somewhere. And if I really need to know, I'll go ask him, or I'll write a program to compute it. So we can get more exact values of pi, right? The other thing that kind of comes up is that now, if I used pi all throughout my program, all I need to do is change it in that one place, and I get more precision all throughout my program. So that's one thing in terms of nice software engineering, right? It changes everywhere, so I don't need to go through and hunt down, oh, where did I put 314 in my program? And I have no inconsistencies, because if everyone's referring to that same constant value, they're all referring to the same thing. The other thing you want to keep in mind, in terms of that reuse, in terms of the good names, is think about names that are readable. No joke, I actually worked on a program at a large corporation once that will remain nameless, where this constant was in the program. And, you know, had the rest of the stuff there. And I looked at that and I was like, yeah, that's very descriptive. 72 equals 72. And I was like, you know, I was really tempted. I just wanted to come along and be like, la, 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 la. Like, does the universe end? Like, what would happen? Like, I have no idea where this is getting used. And it turned out what this was, anyone want to venture a guess what this was used for? It's the number of pixels in an inch on most monitor resolutions. And that's what it was. It was like this GUI program or user interface program. And that's what this was. Because someone somewhere in some class had told them, hey, if you're going to have any values in your program other than 0 and 1, which are very common, and occasionally some other value will come up like you want to divide by 2. It doesn't make sense to say, this is the thing I use to divide by 2 and its value is 2, right? There are some values that come up in your program that it's fine to just have the actual number in there. But other than these things, most numbers that appear in a program actually have some meaning, and you want to have them assigned to a constant. So this person probably heard some rule somewhere that says, oh, you should have a constant for every value in your program. And they didn't know what to name it, so they just called it 72. That's bad. You want to give it real names for what it actually stands for. All right? So any questions about any of this stuff?
You said that the rationale behind like named constant and using that whole private static thing is that nobody can change it. But like to change, if you have like just double pi equals 3.14, you'd still have to go into like the guts of the program. So how is it any better?
Well, the difference between this is that programmatically no one can change it, right? So if I just said double pi equals 3.14, somewhere in my program someone could have come along and written this line, and I can't stop them. Right? So it's bad software engineering because I'm not preventing them from doing this. This actually prevents them from doing this. So if they go into the program and say pi equals 5, when they try to compile, the compiler say, you told me pi was final, now someone's trying to change it. Bad times. So that's the thing. You always want to force other people to also have good practice by doing stuff like this. Question?
Is there a library that we can import that has standard mathematical constants?
There is a math library, but for the purposes of this class, if you're really interested in mathy kind of stuff, come talk to me. But for the purpose of this class, there are some basic functions that are in the book, and so you can use those kind of basic mathy functions. But if you're really interested in other kinds of stuff, we can talk about it separately. I need to push on a little bit, so I'm just going to hold questions for just 1 second, because we need to go to an entirely different topic. And the entirely different topic we're going to go to is something called Booleans. And there was a time when I told you about this type called Boolean, which is just a type for variables whose value is true or false. So we can say Boolean P, and P will take the values either true or false. Anyone know where the word Boolean comes from? Yeah, George Boole. You're like, yeah, Marin, I know that because like his picture's on the cover of chapter 4, right? So know it and learn it. So I should ask you, anyone know how George Boole died? I asked this one. Someone said he got set to false. I thought that was kind of clever. He actually died of pneumonia. And the reason why he died of pneumonia, this is a true story, was that he was out walking one time from his house to the college where he was a professor. And it was in the rain, and he got wet, and he caught pneumonia. And so when he came home, his wife actually, who happened to be the niece of the person who Mount Everest is named for, just totally random side note. History is just fun. So it turns out she had this belief that the way you get over a particular illness is you experience the same conditions under which you got the illness. So she's like, oh, you were like in freezing rain, that's why you got cold? So while he was lying in bed, she would get buckets of ice water and just douse him. And he died. So medicine's come a long way, but hey, true story. All right, so returning to our friend, the Boolean. Boolean has a value true, false, which means what we want to do when we assign something assign a Boolean value to some Boolean variable is we need to figure out some expression that evaluates to true or false, right? It doesn't evaluate to like 5 or 10 or something. It evaluates to true or false. Like 3 greater than 5 is a true-false expression, right? You can look at this and say, but Maron, 3 is not greater than 5. Yeah, and the value of this is false, and that's what gets assigned to P. So there are certain operations we can use called relational operations who, when we evaluate them on 2 values, give us back something that value ostensibly is true or false. So let me show you some examples of that by going to the overhead. Let's see if my little mouse, oh, the remote mouse, I love the remote mouse. So Boolean expressions is just a test basically for a condition, and it evaluates to true or false, right? And you can actually use the words true and false in your program and say P equals true, for example. Those are actually parts of the language. So there's a bunch of different value comparisons you can do, like equal, equal, 2 equals in a row, no space, is equals. It means like, does A equal B? It is not a single equal. What does single equal mean? Assignment, right? When you say x equals 5, that's assignment. When you say x equal y, that is a Boolean expression that evaluates the true if x and y are the same. Not equal is exclamation point equal, or sometimes, now that you're all programmers, after Carol, this is called a bang. Just because it's kind of like loud. It's like bang! Exclamation point, right? Caught your attention. Hopefully you weren't sleeping. If you were, you're not. Bang equal means not equal. And if you're familiar with some other languages where you say like less than, greater than means not equal, not in Java, baby. It doesn't happen. All right, so then there's greater than, less than, greater than or equal to, and less than or equal to. And the order of the symbols for these two actually makes a difference. But as you can imagine, those are some common things you might want to consider for 2 values to see whether or not, or 2 variables to see whether or not, for example, they have equal value. Okay? Now, Boolean comparisons in order of precedence. It turns out there's a bunch of operations you can do on Booleans. There's an operation which is the bang, or the exclamation point, which means not. That's logical not. So if you're a logic person, this is familiar to you. If you're not a logic person, I'll tell you what it means. If you put not in front of some Boolean expression or some Boolean variable like P, if P is true, then not P is false, and vice versa. It just means give me the inverse of the logical value that P has, or whatever that expression would have been. Okay? There's AND, which is ampersand, ampersand. Get to know where the ampersand keys on your keyboard are. This is logical AND. What that means is if I have 2 Boolean expressions, P and Q, they can either be variables or expressions. P and Q is only true if both of the sub-expressions P and Q are both true. If either one is false or both are false, it is false. Okay? And last but not least, there's OR. If you've never used the vertical bar keys on your keyboard, find them. You're like, I may have never used them in my life, and you will probably use them for the first time in this class. And OR, if I have 2 expressions, P or Q, it's true if P or Q or both of them are true. So if either P or Q or both of them are true, then what you get when you take the OR of them is also true. And these are in order of precedence. So your nots get evaluated first, then your ands, then your ORs. Much in the same way that parentheses get evaluated first, then multiplication, division, then addition and subtraction, same kind of thing. So we can look at an expression, for example, Boolean P equals something like this. And notice I've fully parenthesized it to make it a little bit more clear. X is not equal to 1 or X is not equal to 2. So this might be a common thing you might think you want to do if you want to say, well, I want to figure out if X is not equal to 1 and X is not equal to 2. So if it's not equal to 1 or it's not equal to 2, isn't that the right thing? And in fact, this is not the right thing. This is buggy. P will always be true in this case. Why? Because if P is equal to 1, Well, this not equal 1 part is false, but it's not equal to 2, and that becomes true. So you have false or true, and it becomes true, and vice versa if x equals 2. So what you really want to say is x is not equal to 1 and x is not equal to 2. That will make sure, if you want to make sure that x is not equal to 1 and x is not equal to 2, that's how you would write it. Although in English, people tend to say x is not equal to 1 or x is not equal to 2, and so it's confusing if you try to write that out in logic. This is what you really want in that case. This is buggy. Okay? But hopefully this gives you an example of a Boolean expression. So any questions about this? Alrighty, then let's move on. Short circuit of question.
Where you get the or symbol.
Just find it on your keyboard. It depends on your keyboard, but it's a vertical bar. It's somewhere on your keyboard. It will be. And if it's not on your keyboard, throw your laptop away and get a new one. And get angry at someone who ever sold it to you. It's got to be on there. Trust me. Short circuit evaluation, we actually stop evaluating Boolean expressions as soon as we know the answer. What does that mean? Okay, so let's consider something like this. P, which is a Boolean, equals 5 is greater than 3 or 4 is less than 2. Well, you know what? 5 is greater than 3, so as soon as we evaluate that part, that's true. True or anything is true, right? It doesn't matter what the value of this guy is because we already got a true, and true ORed with anything is going to be true. So in fact, Java does an optimization, and the second test is not evaluated at all. That's why it's called short circuit evaluation. As soon as we know the answer, we short circuit out and we don't evaluate the rest of it. And you might say, oh, yeah, Maron, okay, that's interesting. Why should I care? And the reason why you care is there's times making use of this actually makes a difference. So here's a useful example. That's a not so useful example. Here's a useful example. Let's say you want to avoid dividing by 0 because dividing by 0 is an error. You can say, well, p is equal to x is not equal to 0. If x is equal to 0, this is false. False and anything is false, so it won't evaluate the second part over here, and you'll never actually divide by the 0. If x is not equal to 0, this is true. So to know the value of true and something else, it needs to actually come over here and evaluate the second part. Because it got a true for the first part, it needs to know that this is true. But if it evaluated the first part and got past it, you know that x is not equal to 0, so you won't divide by 0. Okay? So these kind of little tricks are actually used sometimes in code, and sometimes it's called a guard to prevent this from happening. But that's why short circuit evaluation is something you should actually know about, because you can actually use it for useful things. Okay? So any questions about that? Any questions about Booleans or the operations or that kind of happy news? Uh-huh.
What happens if you divide by 0?
If you divide by 0, usually you will get an error. You'll get an exception, but we won't talk about exceptions. Just think of it as an error. So let's actually move on. We're just going to cruise through tons of stuff today because life is just good. So it's time for talk about statements. Okay? Just like in Carol, when you had statements like move and turn left and all that happy news, now we're going to do all that happy stuff in Java as well. Okay? So one thing we first need to know about is this thing called a statement block, or a compound statement. They're referred to as the same thing. Usually I say block. The book likes to say compound statement. It's just a set of statements enclosed in braces. So you have some opening brace, a bunch of statements, and then a closing brace. This is what we would refer to as a block. Why do we care about blocks? The reason why we care about blocks is, remember when we declare variables? A variable has something called a scope. All a scope is, the way you can think about it, it's not a mouthwash. The way you can think about scope is that it's the lifetime of the variable. Because variables come into the world when they're declared. And one thing I didn't tell you is that at some point variables die. It's very sad. But where a variable dies and lives is the block in which it is declared. So when we say x equals 5 up here, x is alive until we get to the end of the block in which x was declared, which means when we get to a closing brace, that x goes away. That's its scope or its lifetime. Okay? If we declared x outside of the scope, it would not die when it came here. If x was declared out here, this scope is what's referred to as an inner scope. X is still alive inside the inner scope, and it does not die when we get out. It just dies when we get to the closing brace of the scope in which x was declared. Uh-huh.
When you declare a final end, does it ever die?
It doesn't die because of where we declare it. So if we declare it inside a method, it could die when we get to the end of the method. We're going to declare it in the class, so it's never actually going to be at the end of a method, so it won't die. It'll be alive for the whole time that class is alive. Uh-huh. Uh-huh. Yeah, as long as the variable is declared outside of the subblock, that's fine. And this is kind of a technical point. Sort of in most intents and purposes, you don't need to really worry about the nuances here, but it's just something important to remember, and we'll look at some examples as we go along. So, other statements you should know about. The if statement. You're like, oh, if, it's just like Carol. And yeah, it's just like Carol, right? We say if some condition, and that condition is something that evaluates to true or false. It can be a Boolean variable, or it can be some Boolean expression. Anything that evaluates to true or false. So you can use ands, ors, nots, all that happy news now in a condition, and then you have some opening brace and close brace, just like Carol, and if the condition is true, the statements get executed. So we want to check if something is even. We can say if that number is, when it's divided by 2, is its remainder equal to 0. If its remainder is equal to 0 when it's divided by 2, it's even, so we're going to write out num is even. Now notice here I don't have the braces. And it turns out there's this one special case that says if you have an if statement, and it actually applies to a couple other things, and it's only, the body is only one statement, you don't have to have it inside braces. If it's more than one statement, like this, then you have to have the braces. And so this is just a special case that exists. But I'd like to think of use braces with if. You have to if there's more than one statement inside the braces. But I like to think of something that I refer to as the orthodontist rule, right? What does an orthodontist say when you go to an orthodontist? You need braces, right? It doesn't matter if your teeth are straight or you only have one statement or whatever. You need braces. So it's always a good idea to use braces, which defines a block, right? So this now is a block, even if there's only one statement in the if. There's only one special case that I'll show you in just a second, but in general, always use braces, right? So think orthodontist, always use braces. It's just a good idea, okay? Any questions about if? Hopefully not, because you hopefully were using them a lot with Carol. We have the if-else, just like Carol, right? Same kind of thing going on here. We have some condition. Either we do the statements or we do the else part if the condition is false. So if the remainder of num divided by 2 is 0, we say num is even. Or if the remainder is 0, and if it's not, then we know it's odd, and so we write out num is odd, and so are you. All right? So not a whole lot of excitement going on there. You saw this in Carol. Same thing exists in Java. Now it's just a little bit different, because you're not checking if front is clear anymore, right? We're not in Kansas anymore. You're actually doing some Boolean expression for that condition. Let me give a couple more, and then we'll take some questions. There's something known as a cascading if. This is kind of funky. A cascading if says, what I want is I'm going to check for just one condition to be true. So I'm going to start off with something that looks like a regular if. This is like high school grading, right? If your score is greater than 90, then print out A. Otherwise, else, and what are we going to do with the else? We're going to do another if. Else, if your score is greater than 80, print out B. Else, if your score is greater than 70, print out C, and otherwise it's kind of, well, bad times. All right? So if you think about this, only one of these ifs gets executed. Why does that happen? Because if we come up there and we say score is greater than 90, we do this. We skip the else part. Well, what's the else part? The else part is everything else. Why is it everything else? Because it's an else, and then it's one statement, right? There's no brace here, so remember I told you if you have no braces, it's one statement. Well, what is that one statement? It's an if, followed by an else, and that else has one statement contained within it, so it's part of this bigger if, and that has an else which is contained as part of that if. So all of this stuff, in some sense, all cascades down. So if I do the if part up there, and I don't do the else, I skip over this whole thing. If I don't do the if part, then I come and I evaluate the else, which means I evaluate this first condition. And if it's true, then I print out B and I skip the rest. If it's false, then I evaluate the next condition. So this is just sort of the idiomatic form, or the pattern form that you see. It's called a cascaded if, for when you want to check a bunch of conditions in sequence, and the first one that's true does its if part, and then it skips the remainder of it. Okay, so it's useful for things like grades, where you're like, is it greater than 90? No. Is it greater than 80? No. Is it greater than 70? As soon as I find one, I'm done. And otherwise, I have some catch-all at the end that says, things are bad. All right? So that's the cascading if. There's also something called the switch statement. I'll touch on this very briefly. The switch statement, you can get it in excruciating detail in the book. It's just kind of a nicety to have. You can actually do anything with the switch statement. Anything you could do with the switch statement, you can also do with if statements. So it's just kind of a nicety. The way the switch statement works is it says, if you have some integer value, so here we're going to ask the user for day of the week, right? And the first day of the week is day 0, which is Sunday. So they enter some number, hopefully between 0 and 6. And we say, depending on what number they entered, so that thing that goes inside the parens for a switch statement has to be an integer value. Okay, has to be an integer value. There are some other things later on in the class where we look at the boil down to integer values, but it cannot be a double, interestingly enough. And then we specify, the syntax goes like this: case, then what value matches that case, so this is the case 0, and you have a sequence of statements until you hit something called a break. So notice this is funky because the only braces here are this brace down here and that brace up there, which encloses this whole switch statement. There's no braces in the middle. The way it knows where to stop inside a switch, so if someone enters 0, it says, let me find case 0. Oh, here's case 0. I start executing from this line and keep going until I hit a break. When I hit a break, I jump out here to the end of the closing brace. So if the user types in, let's say 6, it says, is it case 0? No, so it skips that. Is it case 6? Yeah, so it prints out Saturday and then it breaks, which means it skips the default. If they enter any other value other than 0 and 6, it says, does it match 0? No, so it skips that. Does it match 6? No, so it skips that. It comes to the default, which is kind of the be-all if it doesn't match any other cases, and writes out, hey, it's a weekday. Okay? So you can do this with an if, right? But this is just a nice way. There's a lot of times, the idea is to think you have like some mechanical switch and you get to pick one of the options. And that's why it's called a switch statement.
Do you have to go in that order? Or
No, your order can be anything that it wants. You can have, the things can even be out of order, so they don't even need to be sorted. Was there a question in the back? Pardon? You can't break out of the method. All it does is break out of the switch. So it just takes you start executing at that bottom brace again. You don't actually leave the method that you're in. Let's take it offline. Was there another question over here? All right, let's press on then. So in terms of for loops you've also seen before, hopefully in the context of Carol. So we're just zooming through. The way the for loop looks like, here's the general form of the for loop. It has for, just like you saw before in Carol, and now it gets a little bit more complicated, but not much. We have something called the init. What the init is when you come to a for loop, it does whatever statements are in that init once and only once at the beginning of the loop. Okay? Then you have something called the condition. The condition is checked every time before we go through the loop. So the first time we come to a for loop, we do the init, we check the condition. If the condition, which is a Boolean, or it can be any Boolean expression, is true, we execute what's in the loop. If it's not true, we skip over the loop and just execute immediately after that closing brace. Okay, so similar to what you may have done with Carol, for example, except in Carol you probably executed some number of times. And the step, so we execute the statements inside the loop only if the condition's true. And the step is done every time after the loop. Okay, so what does that mean? This is kind of a whole bunch of stuff to keep in mind. Let me just give you a simple example. Here's a loop that you may have written sort of in the Carol world, except now we're going to print out the value of I instead of making Carol do something, right? So this was the form of syntax used for Carol to do something 5 times. Remember that? If you remember that, nod your head. Yeah, hopefully. So what was this really doing? Right now we can pull back the covers. Well, the init was to say, create some new variable named I and set its initial value to be 0. The test you were doing was to say, as long as I is less than 5, execute what's inside the loop. And the step says, every time you go through this loop, I++, add 1 to I and store it back in I. So when we execute this, what happens? The first time it comes to execute, it sets I equal to 0. It checks to see if 0 is less than 5. It is. And it says, OK, I execute the loop. So it prints out a 0, adds 1 to I, and goes back and checks the test. So you can think of the I++ as happening after it's executed the statements in the loop, but before it does the test again. So now it adds 1 to I has the value 1, it's still less than 5, it prints it out, it adds 1 to I, it's now 2, less than 5, it prints it out, adds 1 again, it's 3, it prints it out, adds 1 again, is 4. Now after it prints out 4, it adds 1 to I again. Now I has the value 5. It checks the test again. Is 5 less than 5? No, 5 is not strictly less than 5, so it's done. Okay, so you get the values from 0 to 4. But notice it still went through the loop 5 times. It did the body. We just started counting at 0. And as computer scientists, that's a very common thing to do, is really when you want to count something 10 times, you count from 0 to 9 instead of from 1 to 10. That's just what we do, because 0 is a real number, and we love it, and we care about it. Good question. Exactly. The scope of I is the for loop. So when that for loop, ooh, that was real bad. When this for loop is done, I goes away. Okay? So the lifetime of I is until we get to that next closing brace in the scope in which I is declared. And sort of we think of the scope of I as being the for loop. So when we get to the end of when the for loop is finished executing and we sort of move on down here, I has gone away. But we can create another one in some other loop. That's fine. There's other funkier things we can do with the for loop rather than just counting from 0 up to some value. We can actually start with a value like 6 and count down. So we can say i's initial value is 6. As long as it's greater than 0, subtract 2. So we're going to use sort of that minus equal 2 funkiness. And so when we start off, I starts with the value 6. 6 is greater than 0, so it writes out 6, subtracts 2. 4 is now greater than 0, it writes it out, subtracts 2 again. 2 is greater than 0, so it writes it out again. Subtracts 2 from I, so now I has the value 0. 0 is not greater than 0, so it's done. Okay, so that 0 is not displayed. Because after we do the step, we always check the test again before we execute the loop one more time. Okay, any questions about that? So let's do the while loop super quickly, because you've already seen the while loop in Carol's world. Same kind of thing. While condition, if that condition's true, we execute some statements. The condition's checked before every iteration of the loop, just like in Carol, right? So that's why we did all this stuff in Carol, because it carries all over directly in Java. And we execute the statements only if the condition's true. So let me show you an example. X starts with the value 15 while x is greater than 1. Every time through, we're going to divide x by 2 and write out the value. So first time, x has 15. 15 is greater than 1. We divide by 2. We do integer division, so we get 7. We write that out and go back up there. 7 is greater than 1. We get 3. We do it again. We get 1. When we do 1 divide equal 2, what do we get? 0, which is not greater than 1, so we're done. Okay? Dope. Let me go back. Let me just end the show. All right? So any questions about the while loop? And we'll do our friend the loop and a half next time. All right, so I will see you next week.